Sodium is a popular metal for its high reactivity. There are hundreds, if not thousands, of videos on YouTube of people dropping different sized chunks of sodium into different sized pools of water. And in nearly every case, there's a big boom and lots of laughter. It would be a shame if that's all I did too. Well, okay, it's not all I'm gonna do. And to be honest, this is kind of a dud anyway. There are a few things to point out from a chemistry perspective though. Notice how it balls up as it dances across the top of the water? Well, the reaction with water is producing enough heat to melt the sodium, which is about 98 degrees Celsius. I opted not to include an indicator in the water, but the reaction also produces the very alkaline sodium hydroxide. But when I picked sodium, I knew right away what I wanted to show you. And I knew right away I was going to break my own rules and go buy a chemical I didn't already have in stock. That's right, dry ice. To show you what I want to show you requires some pretty low temperatures, and -78 will do just fine. But before I do all that, I could just stand and stare at the wispy clouds drifting gently off the dry ice for hours. Right. Sodium's most common oxidation state is +1. As far as it's concerned, every atom has an extra electron it wants to get rid of. This makes it a very good conductor of electricity. It also lends itself to a very unique reaction with anhydrous ammonia, and this is the setup to get some anhydrous ammonia. The anhydrous part will be provided by this little device. It's an inline drying tube. The ends pop off, and we can charge it up with a desiccant so the gas passing through will come out at the other end mostly free of water. Take a small bit of cotton and then push it into one of the open ends of the tube. Once you get it in there, you can plug up that end with the hose connection. To the open side, you're going to want to add a little bit of desiccant. In this case, I'm using calcium chloride. Get a funnel, otherwise you'll have calcium chloride all over the place. Put just enough in there so that you can shake it down and fit another cotton plug into the open end. So plug it with cotton, and then put the other hose connection back on that side. Et voila! We have one complete drying tube. Now back to the apparatus. The easiest way to get ammonia gas to be ammonia liquid is by lowering its temperature. It will condense about -33 degrees Celsius. The easiest way to achieve that temperature is with a dry ice acetone bath. Ammonia freezes at -77, and our bath temperature can get as low as -78, which is something to keep in mind. Now, carefully add the dry ice to the acetone bath. Also keep in mind there is a huge temperature difference between these two things. When the very cold dry ice and comparatively very warm acetone meet up, there's some vigorous exchange of heat. There's not a chemical reaction taking place, but the dry ice is subliming at a very rapid rate, and the acetone is much thinner than water and has a lower heat capacity, so it doesn't hold itself together as well under these conditions. What's interesting is how abruptly it stops when the dry ice is gone, then starts right back up again when you add a new chunk. Until the acetone cools down, you're going to have this splashing. It wouldn't be a bad idea to put this into a larger beaker and catch all the splashes. The foam board this was standing on was pretty well destroyed by the acetone. Once it calms down, the objective is to keep the dry ice in supply to avoid it warming up too much. Once there is thermal equilibrium, it's amazingly calm. Now on to the ammonia. To generate ammonia, I'm going to mix solid sodium hydroxide and solid ammonium chloride. Then just add a little bit of water. I measured out enough of the solids to generate something ridiculous like 4 liters of ammonia gas. A good portion of that dissolves in the little water present though. Now before the water goes in, it's really important to insert the tube into the test tube. The air in the system will go through first, but you don't want a lot of ammonia escaping. You want the tube to go just about to the bottom of the test tube, but keep an eye on it so that it's never below the liquid level. This is to avoid suckback when the ammonia gas is no longer being generated. Suckback in this situation isn't as bad as it can be in other experiments, but it does represent significant loss of the product. And by the way, use lots of ventilation. Once the water's in there, you can see it bubbling away, but not very quickly. Adding a little bit more water does get the reaction going, but it represents more loss of ammonia gas since it's going to dissolve in the water. This is after just a minute or two of the reaction going, and you can already see that there's quite a bit of liquid ammonia starting to collect. Seeing how quickly the ammonia was filling up, I decided to pre-cool 2 more test tubes in the ice bath so I could collect all the ammonia that comes over without getting too much in one place. As you can hear, the very cold bath is still unhappy about the very warm addition. I went really slow and managed to keep it under control. The generation of ammonia gas slowed right down, so I figured I'd add a stir bar and a bit more water. At this point, the water in the flask is a very concentrated solution of ammonia. By turning up the heat, I'm hoping to get a little more liquid ammonia. There are loads of places to lose it though. The drying agent is taking out water, which means that it's also dissolving some of the ammonia gas as it passes through. While ammonia gas will dissolve very readily in water, it will also come out of solution very easily with some application of heat. Now that we have the ammonia going, let's not forget we're doing all this for sodium. And here it is. I have a few small pieces already cut and stored in this small bottle, which is also full of mineral oil. And apparently a little built-up pressure too. It's best to work with sodium while it's under mineral oil, or at the very least coated in it. For convenience, I just dumped a little bit out from the storage bottle. It's also important to have an appropriate fire extinguisher handy, especially when working with larger quantities of sodium. Dry sand, with the key word being dry, is the cheapest option. An industrial fire extinguisher powder called Metalex is probably the best option, but it can be hard to find in reasonable amounts, unless you happen to need 50 pounds. For this demonstration, I only need a teeny tiny piece of sodium, since I only have a teeny tiny volume of liquid ammonia. I'm cutting this little piece into 2 smaller pieces, because remember there's a huge temperature difference. Too large a piece of sodium will cause the ammonia to boil away, sometimes violently. It's important to remember 2 exceedingly hazardous materials are being used, not to mention the extreme cold of the cold bath or the highly flammable acetone splashed everywhere. Alright, here's our liquid ammonia. You can see there's a fairly decent quantity here, and it's a good idea to keep it in the cold bath whenever you can. The sodium has a coating of mineral oil on it, of course, and so we need to remove that before throwing it into the ammonia. And there it goes. Almost right away, you can start to see wisps of this dark blue color coming from the sodium. What on earth is going on? Well, remember how sodium has all those extra electrons? In anhydrous ammonia, those electrons leave the sodium and become dissolved in the liquid. They're called solvated electrons, and they're really uncommon. They're also really reactive, and generally awesome. As we watch the solution progress, here are a few fun facts about solvated electrons. They are most commonly observed in solutions of alkali metals in liquid ammonia, like here. This also works well with lithium and potassium and all the other alkalis for that matter. Interestingly, these solutions are stable in liquid ammonia for several days, provided they're kept at the proper temperature. A solvated electron is the smallest possible anion since it is quite literally just a negative charge in solution. This solution, like sodium metal, is of course highly conductive. Alkali metals can also be dissolved in hexamethylphosphoramide, methylamine, and ethylamine to give the same dark blue solution. In addition to the alkali metals, calcium, strontium, barium, europium, and ytterbium dissolve in ammonia to give blue solutions. The most common reaction where this system is used is called the Birch Reduction. In this reaction, aromatic rings are reduced, but not all the way to cyclohexane. As the concentration of solvated electrons increases, you can see the solution is more persistent on the glass. Eventually, you could start to see a copper color. This is what happens when the solvated electrons reach concentrations above 3 molar. As I start to clean up, I leave the test tube at room temperature. The ammonia slowly boils away, and I'm left with a residue of sodium metal and sodium oxides, which needs some special handling to dispose of safely. I start by very carefully and slowly dropping in nearly anhydrous isopropyl alcohol. There's very little reaction, so before too long I end up just dumping it all in. There are some bubbles of hydrogen forming, but it's not very vigorous at all, which is nice. Next, I add a little bit of water, and the reaction speeds up quite a bit. This is a controlled way to dissolve the sodium metal and any oxides. When the reaction slows down, I added a bunch of water and all the gunk dissolved right away. The reaction stayed calm throughout, which was the whole point of adding the alcohol first. At this point, the solution is safe for drain disposal. Before I end this video, the no fire sodium and water demonstration I did earlier was too disappointing, so I'm using a bigger piece. There are a few other things I'd like to do with sodium metal, but this ammonia generation setup took up a lot of time, mostly with trial and error to get it to work properly. I have quite a bit of sodium, and I've had it for quite a while. If my little bottle was under pressure like that, I can only imagine what the big one is going to be like. But that's all going to have to wait for another video on sodium. I'm slightly discouraged though, because even this giant piece of sodium isn't catching fire. I have too much self-respect as a chemist to let it go at this. The part that usually catches fire is the hydrogen, and I thought too much of it was getting away, so why not confine it? And when the fire started, I was pretty happy, until about a second and a half later when I realized the hydrogen is building up faster than it's burning, and eventually there's going to be a point where the ratio of hydrogen and oxygen hits a sweet spot. Cue the mad scientist laughter. I wish I had multiple cameras running. That beaker jumped a good 2 feet, and it was broken long before it landed. Alright, the time has come to see what our next featured chemical is going to be. Oh, there's always a huge clump that comes up to deal with. Okay. Methyl red. Good. This is going to be another opportunity for me to learn something new, and hopefully for you too. Thanks a lot for watching, and I'll see you next time.